So can you see that slide there?
Yes.
Okay. So this example really put the kibosh on the box topology as a topology you don't really want to deal with. So let's see if I can do this. Whiteboard. Okay, so for example, let's think of, so what are we doing? We're in R omega. So this is the space of sequences. So let's think of the sequence 1 on n. So I'm going to call that I'll put a little arrow in. So this is the constant vector 1 on n, right? So it's just 1 on n everywhere. And well, what do we want that to go to as a sequence? What do you think it should go to?
0.
To 0, right? And that does do so, yes, in the product topology, but no in the box topology. And so since the box topology is kind of fine in the product topology, you know, if it was to go to anything, it would go to 0, right? So the fact that it doesn't go to 0 in the box topology means that this sequence is a divergent sequence in the box topology, which is stupid, right? So that's really why you don't want to do anything with the box topology. But anyway, let's go ahead and prove this. So firstly, why does 1 on n, the constant sequence 1 on n, go to 0 in the product topology? So how would we prove that? So let me remind you what it means for xn to go to x. Means, what does it mean? Every neighborhood of x, there exists an capital N such that xn is in a neighborhood U, such that xn is contained in U for all n bigger than that capital N, right? So that's what we think. So that's the general topological definition of a sequence, a series, a sequence converging. Now, why does it do it in the product topology? Well, if we've got a neighborhood, say, of 0, so let's say we have a neighborhood of 0 in box topology. Well, it contains, what does it contain? It contains a set like product of U alphas such that U alpha equals R except for finitely many. Okay, so let that be, let alpha 1 to alpha n be those. And so for those, we can use U alpha equal a ball centered at 0 of radius U alpha I, epsilon I, for instance. Okay, so any open set would contain such a thing. Any open set containing 0. We can find an open set where the non-trivial open sets are balls. Okay, so how do we define then a neighborhood U such that 1 on n is going to be contained in that for all n bigger than for all n some bigger than sub n, right? So what we do is this is a standard argument, right? We just take epsilon equal to the minimum of the epsilon i's, right? And then if we just look at if we look then at what do we want? We want n equaling basically 1 on epsilon, don't we? Does that work?
Or something greater than that.
Yeah. So choose any capital N bigger than 1 on epsilon when epsilon is the minimum, right? And then all 1 on n's are going to lie in that open set. Okay, and so that's the thing. And so what goes wrong in the box topology? So what in that proof for the product topology goes wrong in the box topology?
Well, you might have all those epsilon sub i's. What race it? I guess it could race off to 0 or infinity.
It can go up to 0, right? Because the thing that made it work was this line here, right? And so in the box topology, you would replace the min by a sup, and now you've got no guarantee that that is not 0. Okay, and in fact, if we look at the neighborhood product of 0, no, the product of the balls centered at 0, radius 1 on n. Okay, so let's go n equals 1 to infinity. If you look at this open set here, it doesn't contain any of these vectors up here. Because it's centered at 0, it has radius 1 on n, so the point 1 on n is not in the set, and so this set here does not contain any 1 on n is not an element of this set for any n. And this thing here is a perfectly reasonable open set in the box topology. Does that make sense? Because the thing is, you know, it's this game you play that, you know, first you have to give the 1 on n, and then you give me a 1 on n, I can then find something that's not going to be in it. So okay. So let's stop this. Oops. Let's go back to my thing here. Okay. So so that's actually true for. So what do we want to do? So to show that something is not metrizable, we have to use the show that it breaks the sequence lemma, right? So the sequence lemma said that if something is in the closure of the set, then there is a sequence of elements in that set that converge to that point. Okay, so that means to show that a set is not metrizable, what we've got to show is we have a limit point of a set, so a limit point means it's in the closure but not in the set itself, right? So we have a limit point which is not the limit of any sequence, which is, well, that's why we call them limit points. But So the idea of a limit point is actually kind of false. It's only a limit point if we're in a metric space, right? Because then we can use that epsilon delta kind of argument to get it closer. So let's do that in general then. Okay, so let me go back to the whiteboard then. Whiteboard. Okay, so let's think of the set A, which is the set of points such that all the xi's are strictly positive. So this is a perfectly respectable set in R omega. Okay, and so let's look at the point 0, which is just oops, sorry, it doesn't end. Oops, I should have done that. Just goes on forever. Okay, so the claim is 0 is in the closure of A. And that's pretty straightforward, because what does it mean to be in the closure of A? It means that any neighborhood of 0 intersects A. Well, that's truly true, right? Because if we've got a neighborhood of 0, then it contains something like minus x1 to x1 cross minus x2 to x2, etc. I mean, this is what this is a basic basis element which would be in any open set containing 0. Okay, and trivially, it intersects A, right? It intersects A at the point x1 on 2, x2 on 2, etc. So it's straightforward to show that 0 is in the closure of A. The next point, the second thing then to do, so if we do, call that 1, 2, then is that 0 is not the limit of any sequence in A. Okay, and that's actually, we just kind of just do the example that I did before. We just go ahead and do that. So let's say we've got some sequence. So that means that so if you look at the nth element of the sequence, it's going to look like something like A1n, A2n, A3n, etc. Right? So a sequence in A, of course, is a sequence of sequences. Okay, and let's consider the following basis element in the box topology. We just look at minus A11, minus A11 to A11. So we're going to be using a diagonal argument here. Cross minus A11 2, 2 to A, 2, 2 cross minus A, 3, 3, A, 3, 3, etc. And we just go on that forever. Okay, so what do we got here? So 0 is in B. So this is an open set containing 0. So for it to be a sequence converging to 0, we have to have infinitely, we have to have all the elements being there. But there's no element in that sequence that's in here, right? Because we've deliberately cut it off at A11, A22, A33, etc. So, okay, so that's a nice little thing, and it basically shows that the box topology is kind of useless, really, to do anything in. Any questions about that?
Nope.
It's a pretty nice. Actually, I think it's a pretty nice example. But anyway.
Mm-hmm.
Okay. Let's go to the next example. So. Okay. So let's look at the product topology when J is uncountable. Okay, and so we're going to show a similar thing, that this is not metrizable because this time we're going to let A be the set of all points such that the alpha coordinate is 1, except for finitely many alpha. Okay, and so we're going to do the same kind of thing. We're going to show that 0 is in its closure, but that there's no sequence of points that can possibly go to 0. Okay, so let's do the whiteboard again. Okay, so for example, something we're thinking about a set like R to the R, right? Which is just the set of functions from R to R, which is a perfectly respectable set to consider, right? It shows that you can't put a metric on it, which is kind of annoying. But there are metrics for function spaces. So for example, if you look at the set of functions which are square integrable, so functions for which the integral between minus infinity and infinity of f of x squared square root of that, that's a perfectly good norm on that, and it gives you a metric space. And in fact, have you heard of Hilbert spaces?
Yes.
Okay, so this is an example of a Hilbert space. So this is important in quantum mechanics, for example. So you can put metrics on important subspaces. It's just that you can't put a metric, because if you think about just functions going from R to R, just arbitrary functions, you can realize that can be really badly behaved. So it's not surprising that you can't put a metric on them. Okay, so we're letting A be the set of points x alpha such that x alpha equals 1 for all but finitely many. Oh, sorry, that should be an alpha. Okay, and again, we're going to look at the point 0, which is just the origin, right? Just the constant. Oh, no, it's it's not countable, right? So it's the function that just returns 0 for any input, any index. So we'll just call it 0. Don't worry about what it is. So x alpha equals 0 for all alpha is probably the best way to say that. Okay, so no sequence. So let's do no sequence in A can converge to 0. And I'm thinking you're probably already thinking that this is not a surprise, right? Because what's wrong with A, right? The thing that's wrong with A is that if x alpha equals 1 for all but finitely many alpha, that means x alpha equals 1 for uncountably many indices, right? So there's no way that you can make it converge to 0. So let's go ahead and prove that. So again, let's say we have so the point about sequences, of course, is that they are a countable thing, right? Because you've got AN. So here we've got a sequence in A. So that means for each n, we can let, say, Jn be the indices for which An, how do I write this? An alpha doesn't equal 1. So this is a finite set. And then let's just look at the union of all the Jn's. The union of all the Jn, right, is a countable collection of finite sets. So that's a countable set. So it's a countable set, but in particular, it can't be all of J. So therefore, there exists a beta element of J, which is not in that union of things. So that means every what is it? So that's the nth sequence, and the beta indice of that sequence equals 1. So if we let U then equal the inverse projection of -1, 1, that is a neighborhood of 0, which doesn't contain any ANs, right? Because all the ANs are 1 for those things. So that means AN can't go to 0. Just for uncountable reasons. Okay. Let's see. Oh, I got a little bit of space here. But why is 0 in the closure? So let 0 be in some open set, in some neighborhood. So we're in the product topology. So that means U alpha equals R except for finitely many subsequences. Let's again call it alpha 1 through alpha n. And so let X alpha then equal 0 if alpha does not equal some alpha I. Oh, no. If alpha equals alpha I and equal to 1 otherwise. X alpha is going to be in A, right? Because it's only it's 1 except for finitely many 0, and it's also going to be in this set U, right? Because it's 0 in the places where U alpha is not R, and it's 1 where U alpha equals R, so it's definitely in U. So it's an element of that intersection, A intersected U. So we've got every neighborhood of 0 intersects with A, so that means 0 is in the closure. Oh, sorry. Okay, so you can't put a metric on an uncountable product in the product topology. So those two examples are kind of interesting. So I just wanted to kind of introduce kind of like the next topic, which I think is kind of interesting, which is the idea of quotient spaces. Quotient spaces turn out to be really important in geometry, because what you do is a lot of kind of like really useful geometric objects are sort of constructed from simpler objects. And so then the idea is to try and understand the topology of the constructed object. So here's a definition of a quotient space. So you start off with a topological space, and then you partition it into disjoint subsets whose union is X. So, i.e., you split up into equivalence classes, and you call that set of equivalence classes X star, for instance. So this is going to be our quotient space, and so you have like a natural map from a space to the set of equivalence classes where you just take the point in X and you just take it to its equivalence class. Okay, so that then induces a topology on X star, right? So you just say that open sets in the quotient space X star are just the ones whose inverse image are open in the original space X. Okay, and so that's all you need for a quotient space. And so just for a bit of fun, I'm just going to show you this. So have you heard of RP2? So that's two-dimensional real projective space. So that is the set of lines in three-dimensional space that go through the origin. Okay. And so to get a handle on it, what you can do is then take the normal sphere and you can intersect it with those lines. So like in this picture here. And so if you do that, that means you end up, you get a bijection between lines that pass through the origin in three-dimensional space and antipodal points on the sphere. Okay, and so the quotient space then is just the unit sphere partitioned by antipodal points. Okay, and it turns out to be a really these projective spaces turn out to be really useful in geometry. They have you can generalize them. In fact, you can generalize them to modules, right? You can have projective. You can think about modules where you can think of lines in modules kind of thing, and so you can come up with interesting spaces that way. So, for example, to show you how interesting RP2 is, let's think about loops in RP2. So if you look at this, so there are two kinds of loops in RP2. So remember what a loop is. So a loop is a map from the unit interval to the space such that the endpoints end up at the same point. Okay, and so then you can have that two loops are equivalent if there is like a continuous deformation from one loop to another. So, for example, if you look at that first thing here, where you've got that red line, oh, maybe I should do a little picture. So, if here is our sphere, and we start here and we get a kind of a loop like that, then you can, just by continually deform it, you can make it smaller and smaller and smaller until it gets to be the constant loop. So loops like that you can just think of as zero in the loop space. But there's a non-trivial, so in the sphere, all loops are trivial, right? Because if you're on a sphere, on the surface of a sphere, you've got a loop. You just think of it as a piece of string. You can just pull the string in and make it into the constant loop. But in RP2, if we're here, say at the North Pole, and here's the South Pole, if we travel along a line of longitude from the North Pole to the South Pole, that's a loop, right? Because we've identified antipodal points. So going from the North Pole to the South Pole, that's a loop. And you can think of it in the original space. So if you've got a line, what you can do is on the loop, you then spin that line around until you kind of reverse orientation. So here is your line in three-dimensional space, and you just take that point to that point at the end of the thing, and since it's the same line, that's a loop, right? And so we can call this loop 1. Okay, and a little exercise, what's 1 plus 1 equal to?
2.
It is equal to 2, but what can you do? Well, if you've got a loop from here to here, and I add it to another loop from here to here, it's just concatenation, right? So if you've got a map,
you get one. Or
so the thing then is, once you've done here, you've done there, you can then draw it back in. You know, you can then just in the concatenation, what happens when you know, so you've got a map from 0, 1, and another map to 0, 1, and you concatenate them to get a map from 0, 1 by, you know, this goes to 0, 1/2, and this goes from 1/2, 1, right? And so by adding two loops together, you can then continuously deform it to the trivial loop. So actually 1 + 1 = 0. So the space of loops here is actually Z2. So that shows you that it's a kind of interesting space. Another odd.
So is the idea that, okay, I was just trying to wrap my head around that you've got this like seriously uncountable bunch of lines that have the structure of Z2. Are you saying you can like divide them into two classes or something?
Right, there's only two equivalence classes of loops.
Okay.
There's a trivial class, and of course, you've got to have a base. A loops have to have a base point. So you have some base point that you always go from, because it only makes sense. Concatenation only makes sense if it's a loop from the same spot.
Okay. That
you can add that. And loops have inverses, right? Because you just run the map. You just go from 0, 0. If you've got a map that goes from 0, 1 to your space, then the map is just equal to like u of t minus 1 or something like that. Is an inverse. So you do get a group of loops on this space. And so this is an example. This is in algebraic topology example. So we won't be doing that. We won't get that far. Another interesting example to show you that RP2 is not trivial is, so here's the equator of RP2. Let's cut out a strip around the equator and pull it out. What do we get?
I mean,
so remember, this point here is identified with this point over here.
Okay.
So we only actually have to, it's a band, but to cut it out, we really only have to cut a northern latitude circle out, and a southern latitude circle will be incorporated with it. And so what you get is a Mobius band. So the equator is like a Mobius band. So RP2 is an interesting space. So that you might see in other classes. But anyway. So what do I want to do? Well, yeah, let's just do one more slide. So so that's where we kind of want to go to, but how can we tell we have a quotient space? So let's say we don't have the equivalence relation. How do we sort of construct it just given a map from between two topological spaces? Right, so for it to be for Y possibly to be a quotient space of X, we need the map to be surjective. And it turns out that the requirement that P be a quotient map, i.e. that Y be a quotient space of X, is that any subset U of Y is open in Y, of course, if and only if the inverse image is open in X. Right, so that's a stronger condition than continuity. People often call it strong continuity.
So we didn't have in the definition of a quotient space, P is not a quotient map there, is it?
Sorry?
In the definition of the quotient space,
Right.
that's P is not a quotient.
Quotient space, P will be a quotient map. So if because it's going to be it's surjective. We're given that it's surjective, and the topology is induced by P, and so it's going to turn out that that P will be a quotient map, because it turns out that what's the point, that the map is what we call saturated, which means because it's a equivalence relation, it means that that the inverse image of any point in X star, we pull it back and it gives us the full equivalence class. So yes, so this is so in this case here, P is a quotient.
So it will turn out that the quotient space P is a quotient map, but we don't need to assume that much to get there eventually.
Right. So this is just checking that it is a quotient map. And equivalent definition is that a subset V is closed if and only if the inverse image is closed, and that occurs because of the following thing that right, because the inverse image of Y minus B is X minus the inverse image of B. Just because inverse maps behave well with respect to complements. So anything that is open, its complement is going to be closed. So. Okay. And then finally, another equivalent definition of a quotient map is that the map P is surjective, continuous map, and it maps saturated open sets of X to open sets of Y. And that's what I mentioned before. So we say that a subset is saturated with respect to a map if the subset contains every set of the inverse image of a point that it intersects. Right, so for example, in this example here, a saturated set in the sphere is any set which contains all antipodal points. Right, so a set in this situation is saturated if X, being an element of that subset, minus X is also an element of that subset. So that concept of saturated is important. So I think that's. Oh, and I did have one final example, a surjective continuous map that is either open or closed. So remember, an open map is one that maps open sets to open sets, and it's closed if it maps closed sets to closed sets. So you have a surjective continuous map that is open or closed, and it's a quotient map because it then just satisfies those either the definition or that equivalent definition too. Though you can have quotient maps that are neither open or closed, which I believe is going to be a homework problem. And I think that's where we'll stop for today. And stop recording.